Hi, this is Professor Fernandez. We're going to work on Class Note C in Lesson 15. In this Class Notes, I want to piggyback off what happened in Class Notes A. This is the same system, and in that Class Notes, we just found two vector-valued solutions. So those are the solutions that I've replicated here in red. In this Class Notes, I want to find the general solution of that same system. So we're going to use the concepts and the procedure that we talked about in the previous video. One thing I want to point out, though, I'm going to scroll up here and I'm going to put it in, I'm going to go over this recap. So we talked about in the previous video this procedure, which if I scroll up even further, all my markings are still here, involves a few steps. First of all, the goal is to find the general solution for a system of this form. And the first step is to find n solutions, where n is the same as the size of the matrix or the number of equations in the system, equivalent. To find n solutions, and then you plug in your favorite t-value, and you show that these are linearly independent vectors. And then you just make sure that there are as many as the dimension of the space, or the size of the matrix A, or the number of equations in the system, all equivalent. If you do that, then, as I mentioned in the previous video, you can invoke that procedure, that argument that we developed in that class notes, to conclude that these n solutions really are a basis for the set of solutions to x dot equals ax. Okay, so that argument is fairly general. I do want to mention one thing in this little recap here. I'm recapping how to solve x dot equals ax using linear algebra. So you find the eigenvalues, then you find the eigenvectors, and you do that until you've found all the eigenvectors. And I say you now have n eigenvalue eigenvector pairs. Notice that I'm bringing in a result from the previous few lessons, that if the eigenvalues are distinct, then the eigenvectors are linearly independent. So let me just point out how that ties in to the class notes B argument that we made. So the class notes B argument does not use that. It's actually a more general argument, which is why I wanted to present that first. It does not require that the eigenvalues be distinct. But suppose that the eigenvalues, lambda 1 through lambda n, are distinct, meaning they are not the same. So lambda 1 could be 4, and lambda 2 could be 7. None of the numbers repeat. Then we had this previous theorem, I believe in the lesson that we learned about eigenvalues and eigenvectors. The corresponding eigenvectors, v1 through vn, are linearly independent. Okay, so that's from that theorem that we can go back and find. So why does that help? How does that matter? Well, the solutions that we presume have been found already in this procedure, that's the first 3 steps in the procedure, Vn e to the lambda nt. If I substitute in 0 for t, notice what happens, that at t equals 0, these vector value solutions reduce to just the eigenvectors. And if I know that the eigenvectors are Li by this little result, then I know that the vector value solutions at t equals 0 are Li. So if I scroll back to my theorem, which is this part, I've written it here, but it's in the previous page typed out, then again, that tells me that if they're linearly independent vectors here, then the solutions are linearly independent. So I get the same result, which is that these solutions are linearly independent. And then I can pick up with the rest of the argument in class notes B. I have n linearly independent solutions in an n-dimensional vector space. Therefore, they span the space, and thus they're a basis. So I wanted to point that out here. This is a shortcut. If you have the luck that you're working on a problem where you find the eigenvalues and they are distinct, then this is what I put in the recap as number 4. You can use that to simplify the argument a little bit. And I'm going to show you again how we do that for this example. And we are going to effectively do it both ways, because here, as we've seen, when I plug in t equals 0, I get the eigenvectors, which are related. Their linear independence comes from the distinctiveness of the eigenvalues they came from, if they are distinct. Okay, so back to this example. Find the general solution. Great. So I have found two solutions here. These are the ones that came from class notes A that we found. So what do I need to do? So following my procedure from class notes B, I have to do a couple of checks. So are x1 at t0 and x2 at t0 linearly independent? All right. So this is where you have these two ways to show this. So one way is, let's choose first of all t0, choose a convenient t0. We can choose any of them, right? Choose t0 equals 0. Why? Because then x1 of 0 is just 1, 1. And x2 of 0 is just 1, 4, right? I conveniently get rid of any exponentials in the result. Okay, so in class notes B, right, the more general way to do this, you don't need any assumptions about whether the eigenvalues are distinct. So I would use these two vectors, and I want to check whether they're linearly independent. And now I have at least two ways of doing that if we think back to the linear algebra content. We can form their linear combination, and we can set it equal to the 0, 0 vector, and figure out if this implies that all the c's are 0. We can do that. Or method number 2, we can put these vectors into a matrix and take the determinant. And in this case, the determinant is 4 minus 1 equals 3. If the determinant is non-zero, then we had talked a little while ago in the linear algebra unit about how this implies that the columns of the matrix are linearly independent. And the columns are exactly the vectors that we want to find. We want to determine whether they're Li or not. So this is the simpler way. This matrix way of showing linear independence is the simpler way. But we could have worked this out over here too and found the same result. So these vectors are indeed linearly independent. Let me show you then the second way that I just talked about with this recap in the previous page. So we would say since lambda 1 equals -1 and lambda 2 equals 2 are distinct, then v1 and v2 are Li. All right, and then again, v1 and v2 are exactly, up here, the vector value functions at a convenient t-value. So once again, we answer this question: are they Li? Yes. Okay, and then going back to class notes B in the previous video, the next question we ask is: are there as many vector valued solutions as the dimension of V? And here I'm talking about the space of solutions to the problem we're looking at. Equivalently, the number of equations in the system, equivalently the size of the matrix. So let's scroll up here. So this is a S2 fold. There are two equations in the system. This is a 2 by 2 matrix. The set of solutions to this V has dimension 2. So 2 is the important number here. In this case, 2. And the answer is yes. Scrolling up here, we have found two solutions. There they are. So to wrap everything up, we answer yes. So we say we have found two solutions which are linearly independent. That was by number 1. In a two-dimensional vector space. So they automatically span. Therefore, they're a basis. And thus, every solution is a linear combination of these two solutions. So we can write the general solution as a linear combination of these two. I'm just going to scroll up to make sure I write down the correct, e to the 2t. Great. So this is our general solution. And this is how you would use, you have a choice of which argument you use. I would recommend, if the eigenvalues are distinct, then use this version of the argument, which is why I put it up in the recap. If the eigenvalues are not distinct, then you can use this version, which is a little more general, to show the linear independence portion of the class notes B argument.